Welcome everyone to the second lecture of the time series course. Last week, we looked at stationary time series models for univariate time series, so single time series. This week, we will look at stationary time series models that can be used to jointly model several time series. And these are the so-called vector autoregressive models, or in short, VAR. And the vector autoregressive models, they form a vector or a multivariate extension of the AR models we discussed last week. We will start by discussing the model equation, stability of the VAR, and the maximum likelihood estimation. Then I will continue with hypothesis tests, procedures to determine the lag of the VAR, impulse response functions, Granger causality, and forecasting. First, let's have a look at the VAR model for a stationary n-dimensional vector process, YT. So we have a stationary n-dimensional vector process, YT. Note that I use the small symbol n to denote the dimension of our vector YT. So how many time series we want to jointly model. Hamilton also uses this notation, but please do not confuse it with the sample size n that you might be used to from the regression framework. This is really important. So our stationary vector process YT follows a vector model, a vector autoregressive model of order P, if it satisfies this model equation, where we regress YT on a constant C and on its own past values up until P periods ago. And we have an error vector epsilon T, which collects the n error terms. Now, this looks very much like our model equation of the autoregressive model from last week. Now, we are just jointly modeling a system of equations where we have n constant terms in the model collected in the constant vector C. And our main parameters of interest are now the autoregressive parameter matrices phi1 up until phi p, which are of dimension n times n. They capture the effect of a particular time series on another one at a particular lag. And on the diagonal, we simply have the lagged effects of the time series on itself. On the off diagonal, we have the effects from one series on another. To have a closer look at the model equation of the VAR, consider here this example with three series: inflation, unemployment, and interest rate, let's say. Now, each series gets its own model equation, and we model Y1, Y2, and Y3 jointly. We model Y1 not only as a function of its own lagged values over here, but also as a function of the lagged values of all of the other time series in the system. And the same holds for Y2 and Y3. So in this system of three equations, we clearly see that each equation has the same explanatory variables popping up, namely the lagged values of all series in the model. That's why we can conveniently express this over here through this matrix notation. Now, in the multivariate VAR model, we need to consider also a vector extension of our white noise concept. We still require the expected value of the error terms to be 0. And there is contemporaneous instantaneous correlation allowed between the error terms as captured through this matrix omega over here, which is a symmetric matrix of dimension n times n. but no serial correlation is allowed. So no correlation between the error terms across different time points. So that means that the error term of inflation and unemployment at the same time point t are allowed to be correlated, but not across different time points. Now, several important questions come to our mind when we would like to make use of these VAR models. Namely, how are the concepts of stationarity, of stability defined in the VAR model? How can we estimate the parameters in our model? Which tools can we now use to determine the order P, how many lags should be included in the VAR? And what can we do with these VAR models in practice? Now, let us address these questions one by one, starting with the stability in VAR models. Like we did last week for the AR models, we can evaluate stability of a VAR by rewriting it in companion form, where we stack the p-values of the vector, now yt, on the left-hand side. And we call this new long vector xit. The companion form then writes down the AR1 or VAR1 type of representation for this new vector xit. So we have the vector xit minus 1 at the right-hand side. And the matrix F plays the same role. It ensures that we retrieve our VRP model equation through the first set of equations over here. And the other rows in F just ensure matching of the terms, the lagged values of y that appear both at the left and the right-hand side. The only difference with last week is that on the top rows, we have now the AR parameter matrices. And here we have the identity matrix popping up. Then similarly, if the eigenvalues of this matrix F are small, if they are within the unit circle, then we say that the VAR is stable. And recall from last week then that you can verify this by writing down this characteristic equation where you need to solve for its roots. And if they all fall within the unit circle or are smaller than 1 in absolute value, well, then the model is stable. Now, similarly for the VAR, write down the same p order polynomial, but now we have not scalars, AR parameters, but we have the parameter matrices popping up in front of all of the lambdas. Now, since we need to have a scalar in the end, we should also take the determinant. Finally, under weak stationarity of the error terms and stability of the VAR, one can also prove that the process yt is weakly stationary. Now, a good refresher is to verify these conditions here for this VAR example, as I provided as one of the assignments in the tutorial.